Hello friends, and welcome back to the Snoozy Scientist, where we gently explore the mysteries of our world, one sleepy yawn at a time. Whether you are listening from your bed, curled up beneath a warm nest of blankets, or drifting through that quiet space where thoughts begin to blur, you are exactly where you need to be. Tonight, we are travelling back in time, not to the age of the dinosaurs, although they will make an appearance before this story is through. No. Tonight we are going somewhere older, somewhere stranger, and somewhere far more dramatic than most people ever learn about in school. We are going back 234 million years, deep into a chapter of Earth's history called the Triassic period, and we are going there to witness something almost impossible to believe: a rainstorm. But not the kind that lasts an afternoon, or even a season. This was a rain that lasted nearly 2 million years. Picture that for a moment. 2 million years of rain, not a single unbroken. Downpour, of course, but wave after wave of intense, relentless storms rolling across the planet for longer than the entire span of human civilization multiplied 1,000 times over. Scientists call it the Carnian Pluvial episode. The word pluvial comes from the Latin word for rain, and this episode, this ancient deluge, was one of the most important events in the entire history of life on Earth, even though most people have never heard of it. Before the rain came, the world was a scorched and barren place. A single massive supercontinent called Pangaea stretched from pole to pole, its interior baking under a sun that beat down on endless deserts with almost no relief. Life was struggling, and the planet was still recovering from the worst mass extinction it had ever endured, an event so catastrophic that it had wiped out more than 9 out of every 10 species alive. The survivors were clinging on, but barely. The land was hostile, dry, and punishingly hot. And then, deep beneath the ocean, something stirred. Volcanoes began erupting on a scale that is almost impossible to imagine. Not one volcano, not a dozen, but an entire province of volcanic activity, spanning what is now Western Canada and Alaska, pouring millions of cubic kilometers of molten rock into the sea and pumping staggering quantities of carbon dioxide into the atmosphere. The planet began to warm, the oceans began to heat, moisture filled the skies in amounts the Earth had not seen in millions of years, and the rain began to fall. And what followed was a transformation so complete, so dramatic, that it changed the course of life on Earth forever. The rain killed. It drowned ancient ecosystems, acidified the oceans and drove countless species to extinction. But it also created, from the wreckage of that ancient world, new forms of life began to emerge. Dinosaurs, which had existed for 20 million years as small, insignificant creatures barely clinging to the margins of existence, suddenly exploded in diversity and spread across the globe. The ancestors of modern lizards, turtles, crocodiles, and even mammals began their long journeys toward the forms we know today. The first modern coral reefs took shape in the warming seas. Conifers spread across the land. The very foundations of the world we live in were laid down during those 2 million years of rain. Tonight, we will drift slowly through that ancient storm together. We will feel the heat of the world before the rain. We will stand on the shore of a supercontinent as the first drops begin to fall. We will watch as the landscape transforms from desert to swamp, as old life fades and new life rises, and as the earth remakes itself in ways that still echo in every forest, every ocean, and every creature alive today. But before we begin, if you enjoy videos like this, slow, soothing, and quietly filled with wonder, I would love it if you gave this one a gentle like and maybe tapped subscribe. It helps more curious minds like you find their way to this peaceful little corner of the internet, and lets the algorithm know that sleep and science go perfectly together. And if you would be so kind, let me know in the comments where you are winding down from tonight and what time it is there. It is always a joy to see how far across the world this little sleepy corner of science travels. Now take a deep breath. Close your eyes if you like. Let your shoulders soften and your hands go still. and together let us step back through the ages, past everything we know, past the ice ages and the extinction of the dinosaurs, past the rise of flowers and the splitting of continents, all the way back to a world that was dry and broken and waiting, without knowing it, for the rain that would change everything. This is the story of the time it rained for 2 million years. To understand why the rain mattered so much, you first have to understand the world it fell upon. And that world was unlike anything you have ever seen or imagined. It was a world of one land, one ocean, and almost no water on the ground at all. 234 million years ago, the continents as we know them did not exist. There was no Atlantic Ocean, no Pacific coastline as we would recognize it, no Mediterranean Sea. Instead, every major landmass on Earth was fused together into a single, enormous supercontinent that scientists call Pangaea. The name comes from ancient Greek, meaning all lands, and it is an accurate description. Pangaea was a colossus. It stretched from the northern polar regions all the way down to the southern pole, a continuous slab of land so vast that if you could stand in its centre and look in any direction, you would see nothing but dry earth reaching to the horizon. The shape of Pangaea was roughly like the letter C. Its bulk sat around the equator and spread north and south, curving inward on the eastern side to create a partially enclosed sea called the Tethys, a warm, shallow body of water that would eventually become the Mediterranean. On the outside, surrounding everything, was the Panthalassa Ocean, a single global sea so immense that it covered nearly 70% of the planet's surface. There was water, an unimaginable amount of it, but almost none of it reached the land. This is one of the cruelest features of a supercontinent. When all the land is joined together, the interior becomes impossibly far from the moderating influence of the ocean. Moisture carried by winds from the sea drops as rain along the coastal margins, but by the time those winds reach the deep interior, they have been wrung dry. The centre of Pangaea was a wasteland, a desert of almost incomprehensible scale. Imagine the Sahara, then multiply it by 10, then stretch it from horizon to horizon in every direction, and you begin to approach the reality of what the inner Pangaea looked like during the early part of the late Triassic. The climate was brutally seasonal. Summers in the continental interior were scorching, with temperatures that may have exceeded anything recorded in the modern world. Winters, by contrast, could be bitterly cold, because the same distance from the ocean that prevented rain also prevented the thermal cushion that keeps coastal regions temperate. There were no polar ice caps during the Triassic. The planet was in a hothouse state, with globally elevated temperatures and very little temperature variation between the equator and the poles, but within Pangaea itself, and the swings between summer and winter were violent. Mountain ranges ringed much of the interior, and these acted as barriers, further blocking moisture from penetrating inland. Along the margins of the supercontinent, where the land met the Panthalassa Ocean, there were monsoons. Seasonal winds driven by the enormous temperature differences between land and sea would pull moist air inland, cooling it and dumping heavy rain along the coastlines. But the monsoons were seasonal and limited in reach. The interior remained parched. If you could step into that world, the first thing you would notice is the silence. Not complete silence, but the silence of a landscape stripped bare. There would be no bird song because birds did not yet exist. There would be no buzzing of bees because flowering plants had not yet evolved. And the dominant sounds would be wind moving across rock and sand, the occasional crack of thunder from a distant coastal storm, and the dry rustle of small scrubby plants clinging to whatever thin soil they could find. The vegetation of the Triassic interior was sparse and tough. Small ferns, seed ferns, and primitive conifers dotted the landscape, concentrated around the rare rivers and seasonal water sources. These were not the towering forests of the Carboniferous that had come before, those ancient swamp jungles of giant ferns and club mosses. The great coal swamps had been gone for millions of years, wiped out during the Permian-Triassic mass extinction, the most devastating loss of life in Earth's history. That extinction, which had occurred roughly 15 million years before the time of our story, had killed more than 90% of all marine species and roughly 70% of all terrestrial vertebrates. The world was still healing. Life was rebuilding itself, but slowly, and in a landscape that offered little comfort. The scars of the great dying were everywhere. In the oceans, entire groups of organisms that had been dominant for hundreds of millions of years were simply gone. The great Paleozoic reef systems, built by ancient corals and sponges, had been wiped out, and nothing had yet risen to replace them. The seas were simpler, less diverse, populated by survivors that had managed to cling on through the worst catastrophe life had ever faced. On land, the devastation had been equally thorough. The Permian had been dominated by large mammal-like reptiles called therapsids, but these had been decimated. Only a few lineages survived, including the dicynodonts and the small, inconspicuous cynodonts that were the distant ancestors of true mammals. The ecosystems of the early and middle Triassic were in many ways still recovery ecosystems, populated by opportunistic survivors and the first tentative experiments in new ways of life. It is important to hold this context in mind as we consider what the Carnian Pluvial episode did. The world it struck was not a robust, well-established ecosystem at the peak of its complexity. It was a world that was still fragile, still rebuilding from the worst mass extinction in history. The creatures that lived in the early Carnian were survivors and their descendants, organisms that had already been tested by catastrophe and were only just beginning to find their footing in a new world. And when the Carnian rains came, they hit a biosphere that was vulnerable, still in the process of recovery, and the disruption they caused was magnified by this underlying fragility. The animals that roamed this dry world were an odd assortment. This was the Triassic, which means it was the age of the archosaurs, the group that would eventually give rise to both dinosaurs and crocodilians. But at this point in history, the most prominent land animals were not dinosaurs at all. They were creatures like the rhynchosaurs, stout pig-sized reptiles with powerful beaks that they used to shear through tough vegetation. Rhynchosaurs were everywhere, one of the most successful groups of herbivores on the planet. Alongside them roamed the dicynodonts, the last survivors of an older lineage of mammal relatives called therapsids. Dicynodonts were bulky barrel-bodied animals with tusks and beaks, and they filled the role of large herbivores in many ecosystems. Dinosaurs existed, yes. They had first appeared roughly 245 million years ago, during the recovery from the Permian Triassic extinction. But for the first 20 million years of their existence, they were marginal creatures, small, lightly built and not particularly diverse. They made up only a tiny fraction of the animals in any given ecosystem. If you had visited the Triassic world before the Carnian Pluvial episode and tried to pick out which group of animals would eventually rule the planet for the next 165 million years, you would almost certainly not have chosen the dinosaurs. They were background players, understudies waiting in the wings of a drama whose lead actors seemed firmly established, and the oceans told a similar story of recovery and rebuilding. Marine ecosystems had been devastated by the Permian Triassic extinction, and they were still restructuring. Ammonoids, those coiled-shelled relatives of squids and octopuses, had survived the extinction and were diversifying again. Conodonts, tiny eel-like creatures whose tooth-like fossils are invaluable for dating rocks, swam through the warm seas. Early forms of modern fish were beginning to appear, but the oceans lacked the great reef systems that had characterized earlier periods. The reef-building organisms of the Permian had been largely wiped out, and new reef builders were only just beginning to establish themselves. The sky during the Triassic would have looked different from what we know today. Without the rich oxygen levels of the Carboniferous that had come before, and without the flowering plants that would come after, the atmosphere carried a different quality of light. The carbon dioxide levels were already elevated compared to the modern day, even before the Wrangell eruptions began, and this gave the climate a baseline warmth that kept the poles free of ice and the seas warm to their depths. There were no glaciers anywhere on Earth, no ice sheets, no frozen polar oceans. The planet was in a greenhouse state, and the Triassic interior reflected this in every aspect of its character. Water, where it could be found, was precious. The seasonal rivers that flowed during the brief monsoon months attracted dense congregations of life. Herds of rhynchosaurs would have gathered along the shrinking pools as the dry season advanced, their stout bodies pressing close together, their beaked jaws tearing at the tough roots and stems of plants growing in the damp soil along the banks. Small, agile predators darted among them, and overhead the first pterosaurs, still small and rare at this early stage in their evolution, may have glided on thermal currents rising from the heated earth. But away from the water, the land was empty. The interior deserts of Pangaea were among the most inhospitable environments in the history of the planet. Temperatures in the deep interior may have reached extremes that would be lethal to most modern animals. The absence of vegetation over vast areas meant there was nothing to stabilize the soil, nothing to break the wind, and nothing to provide shade. Sand and dust moved freely across the landscape, driven by winds that had crossed hundreds of kilometers of barren ground without encountering any obstacle. This was the state of the world in the early Carnian, around 234 million years ago, a planet locked in heat and drought, a supercontinent baking under a relentless sun, life clinging on, rebuilding gradually, spread thinly across a hostile landscape. The dominant herbivores were rhynchosaurs and dicynodonts. The dominant predators were large archosaurs that were more closely related to crocodiles than to dinosaurs. Dinosaurs themselves were small, rare, and unremarkable. The oceans were warm, the reefs were sparse, and the interior of Pangaea was a desert of staggering proportions. It was a world that had been dry for so long that dryness felt permanent. The rocks of this period are stained red with iron oxide, the signature of arid conditions. Evaporite deposits, the crystallized remains of ancient salt lakes that had dried up completely, are found across what would have been the Pangaean interior. Sand dunes left their cross-bedded signatures in sandstones that geologists still study today. Everything about the geological record from this time speaks of a planet that was desperately, almost hopelessly, dry. Imagine yourself there, in the very centre of that ancient supercontinent. The air is so dry it seems to pull the moisture from your skin. The ground beneath your feet is hard, cracked, the colour of rust. In the distance, a range of mountains shimmers in the heat haze, their peaks dry and barren. Somewhere far beyond them lies the sea, but it might as well be on another planet for all the good it does here. The sun bears down from a sky that is pale with dust and heat. There is no shade, there is no relief, and there has not been for millions upon millions of years. You are standing in the largest desert the world has ever known, and you have no idea that everything is about to change, because far away, on the other side of Pangaea, beneath the waters of the vast Pantalassa Ocean, something is happening deep within the earth. The mantle is stirring, pressure is building, and a column of superheated rock, a mantle plume, rising from hundreds of kilometers below the surface, is about to punch through the ocean floor and unleash a volcanic catastrophe unlike anything the planet has seen in millions of years. The volcanoes are coming, and with them the rain. And the story of the Carnian Pluvial episode does not begin with a single raindrop. It begins with fire. It begins deep beneath the ocean, in a place that today sits along the western coast of North America, stretching from what is now southern British Columbia through the Yukon and up into south-central Alaska. Geologists call this region the Ranellia, large igneous province, and 234 million years ago, it became the site of one of the most extraordinary volcanic events in Earth's history. To understand what happened, you need to picture the Earth not as a static ball of rock, but as a dynamic, restless planet whose interior is constantly in motion. Beneath the thin crust that we live on, the mantle, a layer of semi-molten rock thousands of kilometers thick, churns slowly in vast convection currents. Heat from the Earth's core drives these currents, and sometimes in certain places a column of unusually hot material rises from the deep mantle like a slow-motion fountain. Geologists call these mantle plumes, and when one reaches the base of the crust, it can trigger volcanic eruptions on an almost unimaginable scale. That is what happened in the Rangelia province. A mantle plume, possibly related to what is now the Galapagos hotspot, rose through the mantle and reached the ocean floor in the Panthalassa Ocean. The results were cataclysmic. Over a period that may have spanned less than 5 million years, the eruptions produced at least 1 million cubic kilometres of basalt. That is enough molten rock to bury the entire United Kingdom under a layer more than 4 kilometres thick. These were not the explosive, conical volcanoes that we typically picture. These were flood basalts, vast outpourings of lava that spread across the ocean floor and built an enormous oceanic plateau, layer upon layer of solidified rock stacking up from the seabed. Some of this eruption happened beneath the waves, producing massive fields of pillow lava as molten rock met cold seawater and froze into rounded bulbous shapes. But much of it also broke the surface, building volcanic islands and plateaus that rose above the ocean. The eruptions were sustained, occurring in multiple pulses over the course of the Carnian stage, and it was not only the lava itself that mattered, it was what the lava brought with it. When basalt erupts, it releases gases, enormous quantities of gases, carbon dioxide, sulfur dioxide, water vapour, and other volatile compounds that had been dissolved in the magma under the crushing pressure of the deep earth are suddenly free to escape into the atmosphere. The Rangelia eruptions pumped staggering amounts of carbon dioxide into the skies. Jacopo Dal Corso, a geology professor at the China University of Geosciences, who has spent years studying the event, described it simply. The eruptions were so huge, he said. They pumped vast amounts of greenhouse gases like carbon dioxide, and there were spikes of global warming. Carbon dioxide is a greenhouse gas. It traps heat in the atmosphere by absorbing infrared radiation that would otherwise escape into space. In small amounts, it is essential for keeping the planet warm enough to support life. But when it is released in massive quantities over geologically short periods of time, then it can drive temperatures up rapidly, destabilizing the entire climate system. And that is exactly what happened during the Carnian. The evidence is written in the chemistry of ancient rocks and fossils. Scientists studying the teeth of tiny creatures called conodonts, which are preserved in remarkable detail in sediments from this period, have analysed the ratios of oxygen isotopes locked within them. These isotopes act as a paleothermometer, recording the temperature of the water in which the conodonts lived. The results show a clear and significant warming during the Carnian Pluvial episode. Global temperatures rose by at least 3 to 4 degrees Celsius, and wider sampling suggests the warming may have been as much as 4 to 8 degrees Celsius. That may not sound like much in everyday terms, but in the context of global climate, it is enormous. For comparison, the difference in global average temperature between now and the last ice age, when glaciers covered much of North America and Europe, is only about 5 to 6 degrees. The warming did not happen in a single smooth wave. Research published in the Proceedings of the National Academy of Sciences in 2021 revealed that the volcanic activity came in at least 4 distinct pulses between approximately 234 and 232.4 million years ago. Each pulse corresponded with a spike of volcanic gases, a shift in carbon isotope ratios in the sedimentary record, and a surge in mercury concentrations in ancient lake sediments. Mercury is a signature of large-scale volcanism, carried into the atmosphere by eruptions, and then deposited across the globe in rainfall and dust. And when scientists find mercury spikes in ancient rocks, they know volcanoes were active. Each of these 4 pulses triggered its own cascade of environmental changes. Carbon dioxide surged, temperatures rose, and then crucially, the hydrological cycle intensified. This is the chain reaction that turned volcanic eruptions into a global rainstorm. Here is how it works. When the atmosphere warms, it can hold more moisture. For every degree Celsius of warming, the air's capacity to hold water vapour increases by roughly 7%. At the same time, warmer temperatures drive more evaporation from the oceans. More water rises from the sea surface, more moisture fills the atmosphere, and more rain falls when that moisture eventually condenses. It is a straightforward relationship, but when amplified across an entire planet over thousands of years, the results are catastrophic. Pangaea was already prone to monsoons. The massive temperature differences between the supercontinent's hot interior and the cooler ocean drove powerful seasonal wind patterns that pulled moist air inland from the Panthalassa Ocean. Under normal conditions, these monsoons were limited, dropping their rain along the coastal margins and weakening as they moved inland. But as the Wrangellia eruptions pumped more and more carbon dioxide into the atmosphere and global temperatures climbed, the monsoons intensified dramatically. The oceans were heating up. Sea surface temperatures rose to levels far above anything in the modern world. One researcher described the Triassic seas as being like hot soup, and while that is a colourful exaggeration, it captures the essential truth. Warmer oceans meant more evaporation. More evaporation meant more atmospheric moisture. More atmospheric moisture meant stronger, more penetrating monsoons. And those monsoons, supercharged by greenhouse warming, began to push deeper and deeper into the continental interior of Pangaea, bringing rain to places that had not seen significant moisture in millions of years. But there was another dimension to this catastrophe that made it even worse. The volcanic gases did not just warm the planet, they also poisoned it. Sulfur dioxide reacts with water in the atmosphere to form sulfuric acid, which falls as acid rain. During the pulses of Wrangellia volcanism, acid rain would have stripped vegetation from hillsides, dissolved exposed rock at accelerated rates, and washed massive quantities of sediment and nutrients into rivers, lakes, and eventually the oceans. The greenhouse gases drove warming and rain. The sulphurous gases drove destruction. Together they created a 1-2 punch that destabilized ecosystems on land and in the sea simultaneously. The onset of this catastrophe may have been startlingly rapid. Some research suggests that the initial shift from dry to wet conditions occurred in as little as 15 to 16,000 years, a geological instant. Carbon cycle feedback effects, where initial warming triggered the release of additional carbon from soils, permafrost, or ocean sediments, may have amplified the volcanic signal and accelerated the climate shift beyond what the eruptions alone could have caused. Once the process started, it fed itself, and growing faster and more intense with each passing millennium. Imagine standing on the coast of Pangaea as this begins to unfold. At first, perhaps, you notice only that the storms are more frequent. The monsoon season seems longer than usual. The winds carry a strange acrid smell, the faint tang of sulphur drifting across thousands of kilometres from distant volcanic vents. The sunsets are vivid, painted in oranges and reds by volcanic aerosols high in the atmosphere. The air feels heavier, warmer. And then the rain begins in earnest, not the familiar rhythmic monsoon that comes and goes with the seasons. Something different, something relentless. Storms that roll in from the ocean and do not stop. Rain that falls for days, then weeks, then months, interrupted only by brief pauses before the next wave arrives, and the rivers that have been dry for longer than any creature can remember begin to fill. Water runs across the cracked desert floor, pooling in depressions, carving channels through ancient sandstone. The land so long parched begins to drink. But the rain does not stop. It keeps coming and coming. The Wrangellia eruptions were not a single event. They were a sustained assault on the atmosphere, lasting roughly 1.6 million years, pulsing in intensity, each pulse driving another surge of warming and rainfall, and the Earth responding to each pulse amplified the signal through feedback loops that kept the moisture cycle spinning long after any individual eruption had subsided. The volcanoes broke the world's climate, and the rain was the result. It is important to understand what the Carnian Pluvial episode actually was and what it was not. It was not a single continuous downpour that lasted without interruption for 2 million years. No raindrop fell for 2 million years straight. What happened was something more complex, more rhythmic, and in some ways more unsettling. The Earth entered a new mode of operation, a state in which the baseline level of rainfall across the entire planet shifted dramatically upward and stayed there, in pulses and waves, for an almost incomprehensible span of time. Think of it less like turning on a faucet and more like changing the settings on a machine. Before the Carnian Pluvial episode, Earth's climate machine was set to dry. The monsoons were limited. The interior of Pangaea was a desert. Rainfall was seasonal and mostly coastal. And then the Rangelia eruptions turned the dial toward wet, and it stayed there. The monsoons intensified. The storms grew larger, more frequent, more penetrating. Wet seasons lengthened. Dry seasons shortened. And between each pulse of volcanic activity, just when conditions might have begun to normalize, another eruption would pump more carbon dioxide into the atmosphere and push the dial further. The rains came in at least 4 major phases, each one tied to a pulse of volcanism from the Rangelia province. Each phase lasted tens of thousands of years. Between the phases, conditions may have eased somewhat, returning partially toward the drier state that had prevailed before, but each successive pulse drove the system further from its old equilibrium, to deepening the wet conditions and extending them over more and more of the planet's surface. By the time the final pulse arrived, the transformation was complete. The world that had been a desert was now a swamp. Close your eyes and try to imagine what this might have felt like, experienced not from the safety of a modern home, but from the perspective of a creature living through it. You are a small reptile, perhaps an early archosaur, sheltering in a shallow burrow at the edge of what was once a seasonal riverbed in the interior of Pangaea. For as long as your species has existed, this river has been dry for most of the year, flowing only during the brief monsoon months before shrinking back to a series of disconnected pools and then vanishing altogether into the sand. The world you know is brown, ochre, rust-coloured, and the plants are tough and sparse. Water is precious and fleeting, but something has changed. The monsoon season came this year, as it always does, but it did not leave. The rains that normally taper off after a few weeks have continued, day after day, week after week. The riverbed that was dry is now a river. The pools that were separate have merged into a continuous flow. The water is rising, not fast, not dramatically, not like a flash flood, just steadily, persistently. The ground that was hard-packed and cracked is now soft. Mud has replaced dust, and the rain continues. At first the change might have seemed like a blessing. More water means more plant growth, more food, more prey for predators. The sparse vegetation along the riverbanks begins to thicken. Ferns unfurl in places where only bare rock had been visible before. Small pools expand into ponds, and ponds merge into lakes. For the first time in the memory of any living thing, the interior of the supercontinent is green. But the rain does not stop, and gradually blessing becomes burden. The soil, which had been baked dry for millions of years, has no structure to absorb this much water. It dissolves. Hillsides that had been stable begin to slump and slide. Rivers that had been gentle now carry loads of sediment so heavy that the water runs brown, then red, then nearly opaque. The acid component of the rain, carrying dissolved sulfur from distant volcanoes, begins to eat at exposed limestone, dissolving it and washing calcium and other minerals into the waterways. The chemistry of every river, every lake, every stream on the planet is shifting. The air itself feels different. It is heavy, saturated, thick with humidity. Even when the rain pauses for a day or two, the moisture does not dissipate. It hangs in the atmosphere, dripping from every surface, condensing on every cool object. Fog fills the valleys. Mist rises from the expanding lakes. The sky is a permanent blanket of grey, low clouds that seem to press down on the land like a wet ceiling. Sunlight, when it comes at all, is diffuse and watery, filtered through layers of cloud and volcanic haze. And the sound. Try to imagine the sound. In a desert, the dominant sound is wind. Wind across sand. Wind through the rare scraggly trees. Wind whistling around rock formations. It is a dry, hissing, whispering sound. Now replace that entirely. The dominant sound of the Carnian world is water. Rain falling on leaves, rain falling on stone. Your rain falling on the surface of lakes that did not exist a generation ago. The constant drip and patter and rush of water moving across, through and over everything. Streams gurgling where there were none. Rivulets cascading down slopes that have never felt the touch of running water. The deep resonant boom of distant thunder, rolling across a sky that never fully clears. For an animal living through this, the change would have been gradual enough to survive from one day to the next, but relentless enough to transform the world within a single lifetime. A creature born in the last years of the dry period might live to see the landscape around it become unrecognizable. The burrow it was born in might be flooded, the hunting grounds it learned to navigate might be underwater, and the plants it depended on for food or shelter might be replaced by entirely different species, moisture-loving ferns and early conifers that thrived in the new wet conditions, but that provided different food, different cover, different everything. The scale of the transformation is staggering. Across the entire supercontinent of Pangaea, the evidence in the rocks tells the same story. Sediments shift from red, arid sandstones to grey, waterlogged shales and siltstones. The minerals in the soil change, reflecting intense chemical weathering driven by abundant rainfall and warm temperatures. Fossilized pollen and spores shift dramatically, from dry-adapted species to moisture-loving plants. Ferns and freshwater algae become abundant in the fossil record for the first time in millions of years. Coal deposits begin to form again. Here the first significant coal since the Permian-Triassic extinction had shut down the great coal swamps 15 million years earlier. The fact that coal was forming tells us that vast swampy environments had returned, places where plant material accumulated faster than it could decompose, building up in thick waterlogged layers that would eventually become the coal seams we find today. Lakes appeared where there had been none. The geological record preserves the sediments of inland lakes that expanded during the Carnian Pluvial episode, their beds recording the cycles of flooding and partial retreat that characterize the rainfall pulses. In the Jiyuan Basin of North China, scientists have studied an ancient lake system that preserved an extraordinarily detailed record of the Carnian Pluvial episode, and the lake sediments show 4 distinct phases of expansion, each one correlating with a spike in volcanic mercury, a shift in carbon isotopes, and a change in the pollen assemblage from dry adapted to wet adapted species. The lake grew, shrank slightly, grew again, shrank, and then grew to its greatest extent during the most intense phase of the event. It is a record of a planet being saturated, pulse by pulse, until the land simply could not hold any more water. Rivers that had been seasonal trickles became permanent torrents. The erosion they caused was immense. Sediment loads increased dramatically as rain and rivers stripped soil from the landscape and carried it downstream. In the oceans, this influx of sediment smothered some marine environments, burying delicate organisms under layers of mud and sand. At the same time, the nutrients carried by all that sediment fertilized the coastal waters, driving blooms of algae and plankton that consumed oxygen and created dead zones in the shallow seas. The forests that began to grow in this newly wet world were different from anything that had come before. Conifers, which had been relatively minor players in the dry ecosystems of the early Triassic, found their moment. They spread rapidly across the landscape, taking advantage of the new moisture regime to colonize vast areas. Some of these early conifers were stressed by the changing conditions, and they responded by producing resin, a thick sticky substance that hardens to amber over millions of years. The Carnian Pluvial episode produced the first major finds of amber in the geological record, and the detail that tells us the trees were struggling even as they spread. Amber production is a stress response, and the fact that it appears so prominently during this period speaks to the intensity of the environmental upheaval. The world was greening, yes, but it was a turbulent, unstable greening, a planet lurching from one extreme to another, from the relentless drought that had defined the early and middle Triassic to the relentless moisture of the Carnian Pluvial episode. There was no gentle transition, no smooth gradient from dry to wet. The change came in surges, driven by the 4 pulses of volcanism, each one hammering the climate system with a fresh injection of greenhouse gases and driving the hydrological cycle to new extremes. And through it all the rain continued, not forever, not without pause, but persistently, insistently, in waves that rolled across the planet for roughly 1.2 to 1.7 million years. The current best estimates place the duration of the Carnian Pluvial episode at somewhere between 1 and 2 million years, with the most intense phases lasting hundreds of thousands of years each. For context, the entirety of recorded human history, every civilization, every empire, every war and invention and migration, spans only about 5,000 years. The Carnian Pluvial episode lasted at minimum 200 times longer than that. Imagine the patience of that rain. Imagine its weight, not violent, not always. Sometimes gentle, sometimes torrential, but always there, always returning, always finding the dry places and making them wet, always filling the low places and raising the water level, always washing the world clean and dirty at the same time, and carrying sediment and acid and minerals and life from one place to another in a ceaseless global redistribution of everything. The rain was not just weather. It was a force of transformation. It was rewriting the map of the world, redrawing the boundaries between land and water, reshaping the chemistry of the oceans, and most importantly, rewriting the story of life itself, because while the rain was falling, creatures were dying. Ecosystems that had taken millions of years to establish were being dismantled, and in the wreckage new opportunities were opening up for the survivors, opportunities that would reshape the history of life on Earth in ways that still echo today. The Carnian Pluvial episode was not simply a change in weather, it was an extinction event. Not as famous as the one that killed the dinosaurs 66 million years ago, and not as devastating as the Great Dying at the end of the Permian. But it was real, it was global, and it reshaped the tree of life in ways that scientists are only now beginning to fully appreciate. For a long time, this extinction was overlooked, even by experts. It was called the hidden extinction, because its signature in the geological record is subtle, compared to the dramatic die-offs that bookend the Triassic period. But recent research has shown that approximately 1/3 of all marine genera disappeared during the Carnian, a significant loss by any measure. The oceans bore the brunt of the damage in some of the most visible ways. The volcanic gases that had triggered the warming and the rain also wreaked havoc on marine chemistry. Carbon dioxide dissolves in seawater to form carbonic acid, and as atmospheric carbon dioxide levels soared during the Rangelia eruptions, the oceans became increasingly acidic. This was devastating for organisms that build their shells and skeletons out of calcium carbonate, the mineral that dissolves in acidic water. Imagine being a creature whose entire body is made of a substance that the ocean is slowly trying to dissolve. That was the reality for countless marine invertebrates during the Carnian Pluvial episode. Conodonts, those tiny tooth-shaped fossils that are so valuable for dating ancient rocks, suffered significant losses. These small, eel-like creatures had thrived in the Triassic seas, but during the Carnian, the diversity crashed. Studies from southwestern China have documented both a reduction in the size and the variety of conodont species during the event, suggesting that the environmental stress was affecting them at the most fundamental levels of their biology. Ammonoids, the beautifully coiled relatives of modern squid and nautiluses, were hit hard as well. These were among the most diverse and widespread marine invertebrates of the Triassic, and they had already survived the Permian-Triassic extinction, but the Carnian brought a new wave of extinctions that significantly reduced their numbers and eliminated many lineages. Crinoids, the graceful flower-shaped animals also known as sea lilies, that had been fixtures of the ocean floor for hundreds of millions of years, suffered major losses. Bryozoans, colonial animals that form intricate and reef-like structures, were decimated. Even green algae, some of the simplest and most ancient forms of ocean life, experienced high extinction rates. The carbonate platforms, those great shelves of limestone that accumulate in shallow tropical seas, shut down. Under normal conditions, these platforms are built by the steady accumulation of calcium carbonate from the shells and skeletons of marine organisms. They are the foundations of coral reefs and shallow marine ecosystems. But during the Carnian Pluvial episode, the combination of ocean acidification increased sediment runoff from the rain-drenched land, and possible episodes of ocean anoxia, where oxygen levels in the deep water dropped to lethal levels, caused these platforms to collapse, and the geological record shows a distinct interruption in carbonate deposition across the Tethys Sea and other marine regions, a gap that corresponds precisely with the timing of the Carnian Pluvial episode. There is evidence that conditions in parts of the ocean became not just oxygen poor, but actively toxic. In some locations, the deep waters appear to have become euxinic, a condition where there is no dissolved oxygen and high concentrations of hydrogen sulfide, a poisonous gas. Manganese concentrations in certain limestone formations from the Carnian increased sharply, which scientists interpret as evidence that the oxygenated zone in the water was shrinking and euxinic. Sulfide-rich water was expanding upward from the depths. For any creature living in these waters, the message was simple: move to shallower water or die. On land, the picture was equally grim, if less immediately dramatic. The dominant herbivores of the pre-Carnian world found themselves in a crisis they could not adapt to quickly enough. The rhynchosaurs, those stocky beaked reptiles that had been among the most successful herbivores on the planet, were devastated by the floral turnover that accompanied the rains. The plants they ate were being replaced. The seed ferns and other dry, adapted vegetation that had formed the basis of their diet were giving way to new plant communities dominated by ferns, conifers and other moisture-loving species. For a rhynchosaur, this was not simply an inconvenience. Their jaws were specialized. Their teeth were designed for specific kinds of plant material. When those plants disappeared, the rhynchosaurs could not simply switch to eating something else, and their biology trapped them. The generalist rhynchosaur lineages that had been common in the Middle Triassic went extinct during or shortly after the Carnian Pluvial episode. Only one specialized subgroup, the Hyperodontines, survived, and they thrived briefly in the immediate aftermath of the event, filling some of the ecological space left by their extinct relatives. But their success was short-lived. Within a few million years, they too would disappear, their highly specialized diets making them vulnerable in a world that continued to change. Dicynodonts, those tusked, barrel-bodied herbivores that were the last surviving representatives of an ancient line of mammal relatives, were reduced in numbers and range. They lingered on for a while longer in some regions, but the Carnian crisis weakened them irrevocably, and the world was moving on, and the ecological niches they had occupied were being opened up for new kinds of animals. The plants themselves underwent a transformation that was swift and dramatic by geological standards. Before the Carnian Pluvial episode, much of Pangaea's terrestrial vegetation was dominated by the Dicroidium seed fern flora, a group of plants well adapted to the dry conditions of the early and middle Triassic. During and after the event, this flora was largely replaced by conifer-dominated ecosystems. The shift was rapid and widespread, recorded in pollen and spore assemblages from every continent, where Carnian age sediments have been studied. Fern spores explode in abundance during the wet phases, a classic signal of environmental disturbance that paleobotanists call the fern spike. Freshwater algae also surge, telling us that standing bodies of water were suddenly everywhere. The floral turnover was not just a change in which plants were growing, it was a restructuring of entire food webs. The animals that had evolved to eat dicroidium and its associated plants were suddenly without food. The predators that had eaten those herbivores were in turn left without prey. The entire trophic pyramid of the Triassic terrestrial world was being dismantled and rebuilt from the bottom up, driven by the relentless change in climate. Insects, too, were affected. While the insect fossil record from the Carnian is less complete than we would like, there is evidence that new groups of insects appeared and diversified during and after the Carnian Pluvial episode, likely in response to the new plant communities that were establishing themselves. And the relationship between insects and plants is ancient and deeply intertwined, and when the flora changes, the insects follow. Even the chemistry of the soil was transformed. The intense rainfall drove chemical weathering to levels far above normal, breaking down rock and soil minerals at accelerated rates and releasing ions into waterways. The kaolinite content of sediments, a clay mineral that forms through intense chemical weathering in warm, wet conditions, spikes dramatically during the Carnian Pluvial episode. This tells geologists that the rain was not just abundant, but was actively dissolving the landscape, reshaping the surface of the continents as surely as it was reshaping the communities of living things. The extinction was not a single sharp catastrophe like an asteroid impact. It was a drawn-out crisis, the unfolding over hundreds of thousands of years, driven by pulse after pulse of volcanism and the environmental chaos that followed. It was insidious. Each pulse weakened ecosystems a little more. Each phase of intense rainfall pushed more species past their breaking points. And between the pulses, when conditions eased slightly, the recovery was never quite complete before the next wave hit. Imagine the slow horror of that from the perspective of the creatures living through it. A rhynchosaur, born into a world where its food plants are already becoming scarce, spends its entire life searching for the tough, dry vegetation its jaws were built to process. But the ferns that are replacing those plants are different, softer, wetter, growing in dense thickets along the new waterways. The rhynchosaur's beak, and so perfectly shaped for shearing through the stems of seed ferns, cannot process these new plants efficiently. It eats less, it grows more slowly, it produces fewer offspring, its young are weaker, and fewer of them survive to adulthood. This does not happen in a single season. It happens gradually, across generations, so slowly that no individual creature could perceive the trend. But the trend is there, relentless, grinding down a lineage that had been successful for millions of years. In the oceans, the process was equally insidious, but operated through different mechanisms. The ammonoids that had been thriving in the warm Triassic seas found their shell chemistry disrupted by the acidification of the water. Calcium carbonate, the mineral from which they built their intricate spiral shells, and becomes harder to produce when the water is more acidic. Each generation of ammonoids expended slightly more energy building their shells, energy that could not be spent on growth, reproduction, or escaping predators. The crinoids, those graceful sea lilies that swayed in the currents on their slender stalks, found the water around them changing in ways they could not accommodate. The sediment raining down from the continents, carried by rivers swollen with endless rain, smothered the substrates they anchored to and clouded the water they filtered for food. One by one, species slipped away, their populations thinning, their ranges shrinking, until they vanished entirely from the fossil record. The scale of this slow dying is difficult to appreciate from the distance of 234 million years. We see it in the statistics, and the 33% decline in marine genera, the disappearance of entire groups of herbivores, the collapse of carbonate platforms, But behind each of those statistics is a living creature that struggled, suffered, and ultimately failed to survive in a world that was changing too fast for its biology to keep up. The Carnian Pluvial episode was not a dramatic apocalypse. It was a long, quiet fade, a dimming of the lights across entire ecosystems, accompanied by the relentless sound of falling rain. For the creatures living through it, the experience would have been one of slow, grinding stress. Not the dramatic terror of a sudden catastrophe, but the quiet desperation of a world that keeps changing in ways that make yesterday's survival strategies useless tomorrow. The watering hole that was reliable last season has become a lake, and the forest that provided shelter has been replaced by a swamp. The food plants have changed, the predators have shifted, nothing is where it was, nothing works the way it used to. And yet, in the midst of all this dying, something extraordinary was happening. Because extinction is never the whole story. For every species that disappears, an ecological niche opens up. For every food web that collapses, a new one begins to form. The Carnian Pluvial episode was destroying the old Triassic world, yes, but it was also simultaneously creating something new, and what it created would turn out to be the foundation of the modern world. Scientists who study this period have given it a remarkable name. They call the Carnian Pluvial episode the dawn of the modern world. That is not an exaggeration. It is not marketing. It is a sober scientific assessment based on decades of research across multiple continents and disciplines. When you look at the list of organisms that either originated or dramatically diversified during and immediately after the Carnian rains, you are looking at the building blocks of every ecosystem on Earth today. Start with the dinosaurs. They are the most famous beneficiaries of the Carnian crisis, and their story is perhaps the most dramatic illustration of how catastrophe can breed opportunity. Dinosaurs had been around for roughly 20 million years before the Carnian Pluvial episode began. They first appeared around 245 million years ago, during the long, slow recovery from the Permian-Triassic extinction. But for most of their early history, they were bit players, small, lightly built and ecologically insignificant. In the fossil assemblages from the Middle Triassic, dinosaurs typically make up only a few % of the total animal community. The world was dominated by other groups of archosaurs, the large predatory Rauisuchians, the armoured etosaurs, the beaked rhynchosaurs, and the bulky Dicynodonts. Dinosaurs existed, but they did not matter much. Then the rains came, and everything changed. The extinction of the dominant herbivores, particularly the rhynchosaurs and many Dicynodont lineages, opened up ecological space that had been locked away for millions of years. The floral turnover that accompanied the Carnian Pluvial episode replaced the old Dicroidium-dominated plant communities with new forests of conifers and ferns, and the herbivores that had been specialised for the old vegetation could not adapt quickly enough. They died, and into the empty niches they left behind stepped the dinosaurs. The evidence comes from multiple lines of research. In the Italian Dolomites, one of the most precisely dated geological sequences from the late Triassic, scientists have tracked the distribution of fossil footprints through the Carnian and Nourian stages. The results are striking. Before the Carnian Pluvial episode, dinosaur footprints are rare. They make up a tiny fraction of the total ichnofauna, the community of animals whose footprints are preserved in the rock. During and immediately after the Carnian Pluvial episode, dinosaur footprints explode in abundance. They go from background noise to a dominant signal in the space of what appears to be a very short time, geologically speaking. In South America, the Ixigualasto Formation of Argentina and the Santa Maria Formation of Brazil preserve some of the oldest well-dated dinosaur body fossils in the world. These formations date to the late Carnian, just after the Carnian Pluvial episode, and they contain a diverse assemblage of early dinosaurs including predatory theropods, long-necked sauropodomorphs, and the earliest ornithischians. The timing is not coincidental. These early dinosaurs were filling the ecological vacancies created by the Carnian crisis. Professor Mike Benton of the University of Bristol, one of the leading researchers in this field, has described the process in clear terms. He noted that dinosaurs originated some 20 million years before the Carnian Pluvial episode, but they remained quite rare and unimportant until the event hit. And it was the sudden arid conditions after the humid episode that gave dinosaurs their chance. The new floras probably provided slim pickings for the surviving herbivorous reptiles, he observed, and the dinosaurs, more versatile and perhaps better adapted to the changing conditions, were able to exploit the opportunities that opened up. This last point is worth lingering on. It was not just the rain itself that helped the dinosaurs. It was the return to drier conditions afterward. The Carnian Pluvial episode was a disruption, a temporary shift to wet conditions and sandwiched between the dry periods that characterized most of the late Triassic. When the rains finally eased and drier conditions returned, the old herbivore communities were gone. The rhynchosaurs were extinct or reduced to a single specialized group. The decinodonts were weakened, and the ecological landscape had been reshuffled, and the dinosaurs, having begun to diversify during the wet phase, were perfectly positioned to take advantage of the new, drier world that followed. They had flexibility, they had adaptability, and now they had space. The expansion of the dinosaurs after the Carnian Pluvial episode was rapid. Within a few million years they had spread across Pangaea, diversifying into new species and filling ecological roles that had previously been occupied by other groups. Sauropodomorph dinosaurs, the ancestors of the great long-necked giants of the Jurassic and Cretaceous, began to take over the role of large herbivore. Theropod dinosaurs, the bipedal predators that would eventually include Tyrannosaurus and the ancestors of birds, started diversifying into a range of predatory niches, and the age of dinosaurs, which would last for the next 165 million years and define the Mesozoic era, was truly born in the aftermath of the Carnian rains. What gave the dinosaurs their edge? Why did they succeed where the rhynchosaurs and decinodonts failed? The answer is still debated, but several factors likely contributed. Dinosaurs appear to have had a more upright posture than many of their competitors, with their legs positioned directly beneath their bodies rather than splaying out to the sides. This gave them greater endurance and efficiency of movement. Some researchers believe that at least some early dinosaurs may have been warm-blooded, or at least had metabolic rates higher than those of their cold-blooded rivals, which would have given them an advantage in the unstable climates of the late Carnian and early Nourian, and their reproductive strategy may also have mattered. Dinosaurs laid hard-shelled eggs on land, which freed them from any dependence on standing water for reproduction. This was a crucial advantage in a world that was oscillating between wet and dry extremes. Amphibians and many other vertebrates still needed water to reproduce, which tied them to specific habitats and made them vulnerable when those habitats shifted. Dinosaurs could nest wherever they found suitable ground, and their young, once hatched, were relatively mobile and could follow their parents to new food sources in a world where the map was being constantly redrawn by changing rainfall patterns. This flexibility was invaluable. There may also have been an element of simple luck, and the Carnian Pluvial episode disrupted the ecosystems in which the old dominant groups had been entrenched. It was not that dinosaurs were inherently superior to rhynchosaurs or decinodonts. It was that the rules of the game changed, and the dinosaurs happened to be better suited to the new rules. Evolution does not design perfect organisms. It favours those that happen to fit the conditions of the moment. And during and after the Carnian rains, the conditions favoured the dinosaurs. But dinosaurs were not the only group to benefit from the Carnian crisis. The list of modern lineages that trace their origins or their initial diversification to this period is remarkable in its breadth. Lepidosaurs, the group that includes all modern lizards, snakes and the tuatara, diversified during the Carnian. Before this time, lepidosaurs were rare and poorly represented in the fossil record. After the Carnian Pluvial episode, they began to spread and diversify, eventually becoming one of the most species-rich groups of terrestrial vertebrates on Earth. Every lizard that basks on a rock today, every snake that coils in the undergrowth, traces its lineage back to ancestors that found their opportunity during or after the Carnian rains. Crocodilomorphs, the ancestors of modern crocodiles and alligators, also began to diversify after the Carnian Pluvial episode. These were not yet the large semi-aquatic predators we know today. The earliest crocodilomorphs were small, lightly built, and often fully terrestrial, but the ecological reshuffling of the Carnian gave them room to evolve, and they would eventually radiate into a stunning diversity of forms, from tiny, cat-like runners to massive aquatic ambush predators. Turtles appeared in the fossil record around this time. The earliest known turtles date to the late Triassic, and their emergence coincides with the environmental changes of the Carnian. Rhynchocephalians, the group that today is represented only by the tuatara of New Zealand, but was once diverse and widespread, achieved a global distribution by the end of the Carnian. Perhaps most remarkably, the ancestors of mammals were also part of this story. The earliest mammalia forms, the tiny shrew-like creatures that would eventually give rise to every mammal on Earth, including us, may have diversified during or shortly after the Carnian Pluvial episode. The evidence is still being assembled, and the timing is debated, but the Carnian crisis opened ecological spaces and created new environmental conditions that may have given these small, warm-blooded creatures the foothold they needed. In the oceans, the transformation was equally profound. Calcareous nanoplankton, microscopic photosynthetic organisms that produce tiny plates of calcium carbonate, made their first appearance in the fossil record during the Carnian. These organisms are today among the most important producers of calcium carbonate in the ocean, and their remains form the White Cliffs of Dover and similar chalk deposits around the world. Their origin during the Carnian Pluvial episode marks the beginning of a new chapter in the history of ocean chemistry and marine ecosystems. Scleractinian corals, the group that builds all modern coral reefs, it underwent their first major diversification during this period. Before the Carnian, reef building was dominated by other groups of organisms. After the Carnian, the Scleractinian corals began to take over, establishing themselves as the primary architects of reef ecosystems. Every coral reef in the world today, from the Great Barrier Reef to the smallest patch reef in the Caribbean, traces its lineage back to the corals that found their opportunity in the wake of the Carnian extinction. Conifers, which had been relatively minor components of terrestrial vegetation before the Carnian, became dominant. The conifer forests that would characterize the Mesozoic era, providing food and habitat for dinosaurs and countless other organisms, were established during and after the Carnian Pluvial episode. Modern conifer families trace their origins to this period. Ferns diversified dramatically, and several modern fern families made their first appearances. The Bonetitalians, an extinct group of seed plants that resembled cycads, and that would become important components of Mesozoic vegetation, also diversified during the Carnian. Even insects were part of the renewal. While the insect fossil record from this period is incomplete, there is evidence that new groups of insects appeared, likely in response to the new plant communities. The deep, ancient relationship between insects and plants, one of the most important ecological partnerships on Earth, was being rewired by the Carnian crisis. There is a phrase that Jacopo Dal Corso used to describe what happened during the Carnian Pluvial episode. He called it a period where extinction was very rapidly followed by a big radiation. A radiation, in evolutionary biology, is a burst of diversification, a time when new species appear at an unusually high rate, filling ecological niches and exploring new ways of life. The Carnian Pluvial episode was both an extinction and a radiation, destruction and creation happening simultaneously, the old world dying and the new world being born in the same breath. It is worth pausing to absorb the full weight of that. If you look around at the world today, at the birds in the sky, the lizards on the walls, the crocodiles in the rivers, the corals in the sea, the conifers on the hillsides, the mammals in the forests, and yes, the insects in the gardens. You're looking at the descendants of survivors and pioneers of the Carnian Pluvial episode. And this 2 million-year rainstorm, triggered by volcanic eruptions in a part of the ocean that no longer exists, shaped the world you live in today. The rain that fell 234 million years ago is still echoing through every ecosystem on the planet. The modern world was born in the rain, and then slowly the rain began to stop, not all at once, not with a dramatic clearing of the skies or a sudden burst of sunshine. The end of the Carnian Pluvial episode was as gradual as its beginning, a slow retreat of the wet conditions back toward the drier climate that would characterize the rest of the late Triassic. The volcanoes of the Rangelia province eventually quieted. The pulses of carbon dioxide that had been driving the greenhouse warming and the intensified monsoon slowed and then ceased. The atmosphere began to adjust. The carbon cycle, which had been thrown into chaos by the eruptions, started to rebalance itself as the excess carbon dioxide was gradually absorbed by the oceans and locked away in new rock formations. The transition was not smooth. Climate does not shift neatly from one state to another. There were oscillations, periods when conditions seemed to be returning to dry, only to be interrupted by another pulse of moisture. The 4 volcanic phases had left their mark on the carbon cycle, and the feedback loops they had triggered took time to wind down. But the overall trajectory was clear. After roughly 1.2 to 1.7 million years of enhanced rainfall, the Earth was drying out again. Imagine what that transition might have looked like. For generation after generation, the rain had been a constant presence. Creatures had been born into a wet world. They had lived their entire lives in a wet world, and had died without ever knowing the dry conditions that their distant ancestors had endured. And now, gradually, the monsoons were weakening. The rainy seasons were growing shorter. The lakes that had filled the interior of Pangaea were beginning to shrink. The rivers that had run full and turbid were slowing, their waters clearing as the sediment load decreased. The swamps that had formed in the lowlands were drying at their edges, their waterlogged soils hardening in the returning heat. Picture one of those shrinking lakes. For hundreds of thousands of years it has been expanding, fed by rivers swollen with monsoon rain, its shores advancing outward across what had once been desert. Fish and amphibians thrive in its waters. Ferns and rushes crowd its margins. Insects swarm above its surface in the humid air. And now, almost imperceptibly at first, the water level is dropping. The mudflats at the lake's edge grow wider each season. The rings of vegetation retreat inward, following the water. The rivers that once fed the lake are running lower, their monsoon surges less powerful. Their dry season flows reduced to trickles. The mud cracks in the sun, forming the characteristic polygonal patterns that geologists will find preserved in stone 234 million years later. Around the drying lake the landscape is shifting. The dense wet forests that had sprung up during the pluvial episode are thinning. Some trees are dying, their roots no longer reaching the water table that once sat just below the surface. Others are adapting, putting down deeper roots, developing tougher bark, becoming the hardy, drought-resistant conifers that will dominate the Mesozoic. The forest floor, once carpeted with soft ferns and mosses, is hardening and drying, littered with fallen needles and the skeletal remains of plants that could not survive the transition. And through this changing landscape, new creatures are moving. A herd of sauropodomorph dinosaurs, their necks extended, their long tails swaying behind them, walks along the margin of the shrinking lake. They are larger than any dinosaurs that existed before the Carnian rains, and they are more numerous. They browse on the new conifer growth, reaching up to strip needles and young branches with their small, leaf-shaped teeth. They are not yet the colossal giants of the Jurassic. Those are still millions of years away. But they are the beginning of that lineage, and the first draft of a body plan that will eventually produce the largest land animals the Earth has ever seen. The forest did not disappear. The conifers that had spread so rapidly during the wet phase were hardy enough to persist in drier conditions, and they continue to dominate much of the terrestrial vegetation. But the composition of the plant communities shifted again, favouring species that could tolerate lower moisture levels. The fern spikes that had characterised the wettest phases of the Carnian Pluvial episode faded from the pollen record, replaced by a more mixed assemblage of drought-tolerant species. For the animals that had survived the extinction and diversified during the wet phase, the return to drier conditions was another test. Some thrived, the dinosaurs, and which had begun their explosive diversification during the Carnian rains, continued to expand and diversify in the drier world that followed. Their physiology, their reproductive strategy of laying hard-shelled eggs that did not require standing water, and their apparent metabolic flexibility gave them advantages that other groups lacked. The sauropodomorphs in particular, those long-necked herbivores that were the ancestors of the great Jurassic giants, spread rapidly across Pangaea in the Nourian stage that followed the Carnian, establishing themselves as the dominant large herbivores on every landmass. Others were not so fortunate. The Hyperodopedontine rhynchosaurs, which had thrived briefly in the immediate aftermath of the Carnian Pluvial episode, found themselves outcompeted as conditions continued to change. Their specialised jaws, once an advantage, now locked them into a narrow dietary niche in a world where the menu was constantly shifting. Within a few million years of the end of the Carnian Pluvial episode, they were gone, the last of their ancient line. The etosaurs, heavily armoured herbivorous archosaurs that resembled oversized armadillos, diversified after the Carnian and became important components of late Triassic ecosystems. Phytosaurs, crocodile-like predators with long narrow snouts, filled the role of large aquatic predators in rivers and lakes. The world was reorganising itself around its new cast of characters, and the drama of late Triassic life was entering a new act. In the oceans, the end of the Carnian Pluvial episode brought a partial recovery of carbonate platform environments, and the shutdown of limestone production that had occurred during the peak wet phases began to reverse as ocean chemistry stabilized and the influx of sediment from the rain-drenched continents decreased. The scleractinian corals that had begun to diversify during the Carnian continued their expansion, slowly building the reef ecosystems that would become one of the defining features of Mesozoic oceans. Calcareous nanoplankton, which had first appeared during the Carnian, continued to proliferate, their tiny calcium carbonate plates accumulating on the ocean floor in vast quantities. The world that emerged from the Carnian Pluvial episode was recognisably different from the one that had entered it. Before the rains, the dominant land animals had been rhynchosaurs, dicynodonts, even large predatory archosaurs more closely related to crocodiles than to dinosaurs. After the rains, dinosaurs were ascending rapidly, crocodilomorphs were diversifying, lepidosaurs were spreading, and the earliest mammalia forms were finding their footholds. Before the rains, the oceans had lacked modern reef systems and calcareous plankton. After the rains, both were established and growing. Before the rains, the vegetation had been dominated by seed ferns and dry-adapted species. After the rains, conifers ruled the land. The transformation was so thorough that some scientists argue the Carnian Pluvial episode represents a more significant turning point in the history of life than many of the more famous mass extinctions. The Big Five mass extinctions, the end Ordovician, the late Devonian, the end Permian, the end Triassic, and the end Cretaceous, are dramatic and well known. But the Carnian Pluvial episode, sitting quietly between the end Permian and the end Triassic, may have been the event that most profoundly shaped the modern biological world. It was, as Dal Corso and his colleagues described it, the dawn of the modern world, and that dawn was painted in rain. Let us pause here for a moment. Let your mind rest on that image, a world remade by water, deserts turned to swamps and then slowly back to something drier, but never quite the same. New forests growing where bare rock had been, new animals walking paths that had not existed a million years before, new corals building reefs in oceans that had been barren. The whole living world reshuffled, reorganized and set on a new trajectory that would lead eventually through the age of dinosaurs, and through the age of mammals, through the ice ages, through the emergence of our own species, to the moment you are in right now. The rain that fell 234 million years ago is not just a geological curiosity, it is part of your story. The dinosaurs it helped to rise would eventually give rise to birds. The mammalia forms it helped to establish would eventually give rise to you. The coral reefs it seeded are still growing in tropical seas. The conifers it spread still cover vast portions of the planet. The echo of that ancient rain reaches all the way to this moment, to this quiet room where you are listening, drifting gently towards sleep. You might be wondering as you lie there in the comfortable quiet of this evening how on earth we can know any of this. How do scientists reconstruct a rainstorm that happened 234 million years ago? How do you prove that it rained on a supercontinent that no longer exists, in an atmosphere that no longer exists, on a world that has been utterly remade since? It is a fair question, and the answer is one of the most beautiful stories in modern geology, because the discovery of the Carnian Pluvial episode was not a single eureka moment. It was a slow, painstaking detective story that unfolded over decades, pieced together by geologists working in different countries who did not initially realize they were looking at the same event. The first clues appeared in the 1970s, in the mountains of Austria. Two geologists named Schlager and Schollenberger were studying the northern limestone Alps, a spectacular range of mountains built from layers of ancient rock that record hundreds of millions of years of Earth history. Most of the rock from the late Triassic period in this region is carbonate, limestone and dolomite, formed in warm, shallow seas under dry conditions. It is the kind of rock you would expect from a world dominated by desert and arid climate. But Schlager and Schollenberger found something that did not fit. Within the otherwise uniform sequence of carbonate rock, there was a layer of dark grey siliciclastic sediment. Siliciclastic means made of fragments of silicate minerals, the kind of sediment that forms when water erodes the land and carries the broken down particles into the sea. In a dry world, you do not get much siliciclastic sediment in marine environments because there is not enough rainfall and runoff to wash material off the continents and into the ocean. But here, embedded within the dry period rocks, there was a distinct layer that spoke of wet conditions, very wet conditions. At the time, it was a curious anomaly, a single finding in a single location, but then similar discoveries began to appear elsewhere. In England, geologists studying the Mercia Mudstone Group, a sequence of red, arid environment rocks from the late Triassic, found interruptions, grey beds, evidence of increased water flow, changes in the types of minerals present that pointed to enhanced chemical weathering under humid conditions. In Italy, in the Dolomites, researchers noticed shifts in the rock record that coincided with changes in the fossil assemblages. The patterns were starting to converge. The breakthrough came in 1989, and when two British geologists named Michael Sims and Alistair Ruffle published a paper that pulled all of these scattered observations together into a single, coherent hypothesis. Their insight was elegant and powerful. Sims, who was studying the extinction of crinoids in the Carnian, and Ruffle, who was investigating the lithological changes in the Mercia Mudstone Group, had a conversation at Birmingham University on the 10th of November 1987. In that conversation they realised that the geological evidence for climate change that Ruffle was seeing in the rocks was happening at exactly the same time as the biological evidence for ecological disruption that Sims was seeing in the fossils. The two data sets were independent. Neither had been used to infer the other, and yet they pointed to the same event. Sims and Ruffle named it the Carnian Pluvial episode, and they propose that it was a period of significantly increased rainfall during the Middle Carnian, driven by some combination of oceanic or volcanic instability. At the time, they did not have the evidence to identify the specific cause. That would come later. But they had established the framework. The idea that the Carnian stage of the late Triassic contained a distinct and globally recognizable episode of wet climate that disrupted both the physical environment and the biological communities. For the next 2 decades, the Carnian Pluvial episode remained a relatively obscure topic, known to specialists but largely ignored in broader discussions of mass extinctions and climate change. It did not fit neatly into the established narrative of the Big Five mass extinctions, and the evidence, while growing, was still patchy and scattered. The Carnian was, as one researcher put it, the research topic of a very small community of scientists. That began to change in the 2000s, as new analytical techniques and new discoveries brought the Carnian Pluvial episode into sharper focus. One of the key breakthroughs came from carbon isotope analysis. When volcanic eruptions release carbon dioxide into the atmosphere, the carbon carries a distinctive isotopic signature. It is lighter, meaning it contains a higher proportion of the lighter isotope carbon-12 relative to the heavier carbon-13. This signature is recorded in the rocks and fossils of the time, creating what geologists call a negative carbon isotope excursion, a dip in the ratio of heavy to light carbon that acts like a fingerprint of volcanic degassing. Jacopo Dal Corso, working at the China University of Geosciences, was among the first to identify a major negative carbon isotope excursion in the Carnian that could be linked to the eruption of the Erangelia Large Igneous Province. In a paper published in 2012, he and his colleagues demonstrated that the isotopic signature in Carnian rocks matched what you would expect from a massive release of volcanic carbon dioxide. Subsequent work showed not one but 4 separate negative carbon isotope excursions during the Carnian Pluvial episode, each one corresponding to a pulse of volcanism. The smoking gun had been found. Mercury provided another crucial line of evidence. Volcanic eruptions release mercury into the atmosphere, and this mercury is distributed globally by atmospheric circulation before being deposited in sediments. Mercury concentrations in ancient rocks can therefore be used as a proxy for volcanic activity, even millions of years after the eruptions themselves. When scientists analysed mercury levels in Carnian Age lake sediments from the Jiyuan Basin in North China, they found 4 distinct mercury spikes that correlated precisely with the 4 carbon isotope excursions and the 4 phases of enhanced humidity recorded in the pollen and mineral data. The correspondence was remarkable. 4 eruptions, 4 carbon spikes, 4 mercury spikes, 4 wet phases. The chain of cause and effect was clear. The evidence has since been found across the world, from the Dolomites of northern Italy, and where the stratigraphy is some of the most precisely dated anywhere in the Triassic, to ancient lake beds in China, to terrestrial sediments in South America, to marine rocks in the Tethys and Panthalassa oceans. The fingerprints of the Carnian Pluvial episode have been identified on every continent where Carnian Age rocks are preserved. The event was truly global, a planet-wide disruption that left its mark in the chemistry, the mineralogy, the paleontology and the sedimentology of rocks spanning tens of thousands of kilometres. One of the most evocative lines of evidence comes from the fossilised pollen and spores preserved in Carnian sediments. Palynologists, scientists who study ancient pollen, can reconstruct the plant communities of the past by identifying the distinctive shapes and textures of pollen grains and spores. In Carnian Age sediments, the pollen record shows a dramatic shift. Before the Carnian Pluvial episode, the assemblage is dominated by dry adapted species, the kinds of plants that thrive in arid environments. During the event, the record floods with fern spores and freshwater algae, exactly what you would expect in a world suddenly drenched in rain. After the event, the assemblage shifts again, reflecting the new conifer-dominated ecosystems that replace the old vegetation. These tiny grains of pollen, each one smaller than the period at the end of a sentence, carry within them the story of an entire world being remade. A scientist sitting in a laboratory, peering through a microscope at a speck of fossilized plant material, is reading a message sent across 234 million years. A message that says the rain came and everything changed, and the Dolomites of Italy deserve special mention. These magnificent mountains, a UNESCO World Heritage Site, famous for their dramatic peaks and pale golden stone, are one of the most important windows into the Carnian Pluvial episode. The rocks here were formed in a shallow tropical sea on the margin of the Tethys Ocean, and they record the Carnian in extraordinary detail. The stratigraphy is thick, well exposed, and has been precisely dated using a combination of biostratigraphy, magnetostratigraphy, and astrochronology, the use of astronomical cycles to calibrate the geological timescale. It was in the Dolomites that the Carnian Pluvial episode was dated most precisely, to an interval between approximately 234 and 232 million years ago. And it was in the Dolomites that the first dinosaur footprints appear, and exactly at the time of the event, providing some of the most compelling evidence for the link between the Carnian rains and the rise of the dinosaurs. Think of it. The proof of one of the most important events in the history of life on Earth is written in mountains you can visit, in rocks you can touch, in fossils you can hold in your hand. The Carnian Pluvial episode is not a theoretical construct or a mathematical model. It is real, physical, preserved in the substance of the Earth itself. And it took decades of careful, patient work by scientists in Austria, England, Italy, China, Argentina, and beyond to recognize it, to piece it together, and to understand what it meant. This is one of the things that makes geology so beautiful. The Earth keeps records, not in books, not in writing, but in rock. Every layer of sediment is a page. Every shift in mineral composition is a sentence. Every fossil is a word. And if you learn to read them, the stories they tell are more astonishing than anything fiction could invent. Now let us do something different. Let us leave the science behind for a little while and simply be there. Close your eyes if they are not already closed, and come with me. Let me take you to the edge of the Tethys Sea, somewhere on the eastern margin of Pangaea, roughly where southern Europe sits today, at the very beginning of the Carnian Pluvial episode. The rain has just started. The air is warm, warmer than anything you have felt. The kind of warmth that does not just surround you but presses against you, heavy and close, like wearing a blanket in summer. The humidity is extraordinary. Each breath feels thick, as though the air has been mixed with steam. Your skin is damp the moment you step outside, not from rain, not yet, but simply from the moisture in the atmosphere. It is the kind of humidity that makes you aware of every pore, every fold of fabric, every surface that the air touches. The landscape around you is low and flat. You are on a coastal plain, not far from the sea. Behind you, the land rises gently toward the distant interior of Pangaea, but the mountains that ring the supercontinent are far away, barely visible as a faint blue smudge on the horizon. In front of you, the Tethys Sea stretches to the east, its surface a strange milky blue-green. The water is warm, very warm. You can feel its heat radiating even from the shore. The beach, if you can call it that, is made of fine pale sand and broken shells, mixed with the remains of tiny marine organisms that have been washing up here for millennia. The vegetation along the coast is sparse but present. Small ferns cluster around the mouths of seasonal streams. A few stunted conifers lean away from the prevailing wind, their branches thin and their needles yellowed by the heat. Further inland, the landscape turns brown and dry, the familiar ochre of the Triassic desert that has defined this part of Pangaea for millions of years. But here, at the coast, there is just enough moisture from the sea to support life. You look up. The sky to the west is different today. It has been different for a while, actually. For the past several years the sunsets have been spectacular, bands of orange and crimson and purple painted across the horizon by volcanic aerosols drifting through the upper atmosphere from eruptions far to the west on the other side of the ocean. You have noticed, though you could not explain it, that the air has a faint acrid quality to it, not strong, not alarming, but present, a metallic tang at the back of your throat. Sulphur, carried across thousands of kilometres by the prevailing winds, and today the sky to the west is darker than usual, not the darkness of night, but a deep heavy grey. Clouds are building along the horizon, piled high and thick, their bases flat and dark, their tops billowing upward into the haze. You have seen storm clouds before. The monsoon brings them every year, great towering banks of cumulus that march inland from the sea, dump their rain along the coast, and then dissipate before reaching the interior. But these clouds are different. There are more of them, they are larger, and they are moving faster. The first drops of rain land on the sand around you. They are warm, almost the temperature of the air itself, and they leave dark circles on the pale ground. The pattern is random at first, a drop here, a drop there, the hesitant opening of a storm still gathering its strength. Then the intervals shorten, the drops grow larger, the sound of them begins to build, a soft pattering that grows louder, steadier, more insistent. Within minutes the sand is dark with moisture. Within an hour shallow puddles are forming in the low places. The stream mouths are running higher. The rain does not stop. As the hours pass, the storm intensifies. The wind picks up, driving the rain sideways in sheets, and the sky is a uniform grey now, ceiling to horizon, the sun reduced to a vague diffuse glow that provides light but no warmth, beyond what the greenhouse atmosphere already supplies. The temperature does not drop, as it might during a storm in our world. The air remains warm, even hot, and the rain falls through it like warm bath water. By the end of the first day the landscape has changed. The seasonal streams, which had been dry or barely trickling, are running full. The pools that dotted the coastline are expanding, their edges creeping outward across the sand. The ferns along the stream banks are bowing under the weight of water, and still the rain falls. By the end of the first week, the coastal plain is saturated. Water stands in shallow sheets across the flat ground. The streams have become rivers. The sound of running water, and which had been so rare in this dry world, is now constant, a background murmur that accompanies everything. Insects that had been dormant, waiting for moisture, emerge in swarms. Amphibian-like creatures, primitive tetrapods that had been sheltering in burrows along the coast, come out to hunt the insects. The ferns are growing visibly, unfurling new fronds at a rate you can almost see. By the end of the first month, the landscape is unrecognisable. Where there was desert, there is now marsh. Where there were dry stream beds, there are rivers. The sea itself seems different, its surface whipped by constant wind, its colour changed by the influx of sediment from the rivers. The rain has eased slightly, the first storm giving way to a steadier, more rhythmic pattern of precipitation, but it has not stopped. It has simply settled into a new normal. Every day the clouds build in the afternoon. Every evening the rain comes, sometimes light, sometimes heavy, but always there. And this goes on, not for another week, not for another month, but for years, for decades, for centuries, for tens of thousands of years. The pattern shifts, intensifies, eases and intensifies again as each new pulse of volcanic activity from the Rangelia province sends another surge of carbon dioxide into the atmosphere and another round of enhanced moisture into the hydrological cycle. Lakes form in the interior of Pangaea, where none have existed in living memory. Rivers carve new channels through sandstone that is millions of years old. Swamps spread across lowlands that had been desert for as long as any geological record can recall. The world is drowning. Slowly, yet patiently, relentlessly, not in a single flood, but in a ceaseless accumulation of water, drop by drop, storm by storm, season by season, century by century. The rain is patient. It has millions of years. And if you are finding this imagery soothing, if the thought of gentle warm rain falling on an ancient world is helping your mind to settle, and your body to relax, then you are in good company, because there is something deeply calming about rain, something that reaches into the oldest parts of our brains and whispers that it is time to rest. Water is safety, water is life, and the sound of rain, even imagined rain from 234 million years ago, carries a peace that is difficult to find anywhere else. So let the rain continue to fall in your mind. Let it wash over the ancient landscape. Let it fill the rivers and the lakes, and let it feed the new forests and the new coral reefs. Let it carry the world from one age to another, and while it does, let your breathing slow, let your thoughts drift. The rain does not need your attention, it falls on its own. When we study events like the Carnian Pluvial episode, it is tempting to treat them as curiosities, interesting stories from deep time, safely locked behind hundreds of millions of years of geological history, something that happened so long ago, in a world so different from our own, that it could never have any relevance to the present. But that temptation is misleading, because the Carnian Pluvial episode is not just a story about the past, it is a mirror, and if we look into it carefully, we can see reflections of our own time staring back at us. The fundamental mechanism behind the Carnian Pluvial episode is one that we understand very well, because it's the same mechanism that is at work in our world today. Carbon dioxide is released into the atmosphere warms, the hydrological cycle intensifies, weather patterns shift, ecosystems are disrupted, species that cannot adapt go extinct. Species that can adapt survive and diversify, filling the ecological spaces left behind by those that could not keep up. During the Carnian, the source of the carbon dioxide was volcanic. The Rengelia Large igneous province pumped greenhouse gases into the atmosphere over a period of roughly 1.6 million years, driving global temperatures up by 4 to 8 degrees Celsius and transforming the climate of the entire planet. The eruptions were natural, involuntary, yet the product of forces deep within the earth that no living thing could control. And yet their effects were devastating. 33% of marine genera were wiped out. Entire groups of terrestrial herbivores went extinct. The floral composition of the planet was overhauled. Oceans acidified, reefs collapsed. The world was fundamentally remade. Today the source of the carbon dioxide is different. It is not volcanic, it is industrial. The burning of fossil fuels, the clearing of the forests, the manufacture of cement, and 100 other human activities are releasing carbon dioxide into the atmosphere at rates that are, by some measures, comparable to the most intense phases of volcanic degassing in Earth's history. The parallels are not perfect, because no analogy ever is. The timescales are different. The starting conditions are different. The specific organisms affected are different, but the underlying physics is the same. More carbon dioxide means more warming. More warming means more evaporation. More evaporation means more intense precipitation in some regions and more intense drought in others. The hydrological cycle accelerates, and the consequences cascade through every ecosystem on the planet. Scientists who study the Carnian Pluvial episode are keenly aware of these parallels. When Jacopo Dal Corso and his colleagues published their comprehensive review of the event in 2020, they explicitly noted its relevance for understanding modern climate change. The Carnian Pluvial episode shows us what happens when the carbon cycle is disrupted on a global scale. It shows us that the consequences are not confined to one region or one group of organisms. They are planetary. They affect everything from the smallest plankton in the ocean to the largest herbivores on land, and they can reshape the trajectory of life on Earth for millions of years afterward. One of the most important lessons from the Carnian Pluvial episode is that the Earth's climate system is not linear. It does not respond smoothly and proportionally to changes in atmospheric composition. Instead, it is full of feedback loops, tipping points, and threshold effects that can amplify small changes into enormous consequences. The initial volcanic carbon dioxide emissions from regalia may have been the trigger, but the response was magnified by feedbacks. Warming oceans released additional carbon dioxide from dissolved stores. Thawing permafrost, if it existed at high latitudes, may have released methane, another potent greenhouse gas. Changes in vegetation cover altered the albedo of the land surface, changing how much sunlight was absorbed versus reflected. Each of these feedbacks pushed the system further from its original state, creating a cascade of changes that was far larger than what the volcanic emissions alone would have produced. We see similar feedback loops in operation today. Arctic sea ice is melting, exposing dark ocean water that absorbs more sunlight and accelerates warming. Permafrost is thawing, releasing methane and carbon dioxide that had been locked away for thousands of years. Forest fires are increasing in frequency and intensity, releasing stored carbon and reducing the capacity of forests to absorb future emissions. And the parallels are not hypothetical. They are real, measurable, and accelerating. Another lesson from the Carnian Pluvial episode concerns the relationship between extinction and renewal. The event was both destructive and creative. It wiped out a third of marine genera and eliminated several major groups of terrestrial animals. But in doing so, it opened ecological space for new groups, including dinosaurs, modern reptiles, modern corals, and the ancestors of mammals, to diversify and establish themselves. The extinction was not just an ending, it was a beginning. This dual nature of environmental disruption is something we should think about carefully. In our own time, we are witnessing an acceleration of extinctions driven by climate change, habitat destruction, pollution, and other human activities. Species are disappearing at rates far above the normal background rate, and ecosystems are being simplified and degraded across the globe. It is a crisis, and it should be treated as one. But the Carnian Pluvial episode reminds us that life, as a whole, is extraordinarily resilient. It will survive in one form or another. The question is not whether life will continue, but what form it will take, and whether the world that emerges from the current disruption will be one that we recognize and can thrive in. The Carnian also teaches us about the speed of recovery. After the rains ended and drier conditions returned, it took millions of years for new ecosystems to fully stabilize. The dinosaurs did not become dominant overnight. The new coral reefs did not spring up in a single generation. The reorganization of the biosphere was a long, yet complex process that played out over geological timescales. If we are disrupting our own biosphere on a comparable scale, we should not expect a quick recovery. The damage we do today may take thousands, tens of thousands, or even millions of years to heal. We are living within a geological instant, but our actions are writing chapters that will be read in the rock record for millions of years to come. There is a poignancy in this connection between past and present. The Carnian Pluvial episode was an involuntary catastrophe, driven by forces no living thing could have anticipated or controlled. The volcanoes erupted because the Earth's mantle was behaving as it always does, driven by heat and pressure and the slow, relentless physics of convection. There was no choice involved, no awareness, no possibility of intervention. Our situation is different. We know what is happening. We understand the mechanisms. We can measure the carbon dioxide accumulating in the atmosphere. We can model the consequences with increasing precision. We have the knowledge and, arguably, the technology to alter the trajectory. The Carnian's creatures had no warning and no choice. We have both, but the Earth does not care about our intentions. It responds to physics, not politics. If the carbon dioxide levels rise, the atmosphere will warm. If the atmosphere warms, the hydrological cycle will intensify. If the hydrological cycle intensifies, weather patterns will shift, ecosystems will be disrupted, and species will be forced to adapt. Migrate or die. The Earth responded to the Rangalia eruptions with absolute mechanical faithfulness. following the laws of physics to their inexorable conclusions. It will respond to our emissions with the same indifference. The Carnian Pluvial episode lasted roughly 1 to 2 million years. Our industrial emissions have been significant for only about 200 years. In geological terms, we are at the very beginning of our own experiment with the carbon cycle. The first drops of our particular rainstorm are just beginning to fall, and we do not yet know how heavy the rain will become or how long it will last. But the Carnian gives us a window into what a fully disrupted carbon cycle looks like, and the view is sobering. There is also quite a more personal lesson in the story of the Carnian rains. It is a lesson about the relationship between destruction and creation, between endings and beginnings, and between the death of what was and the birth of what could be. The Carnian Pluvial episode was a catastrophe, yes. It killed and disrupted and destroyed. But it was also the opening act of the modern world. Without it, there would have been no age of dinosaurs, no age of mammals, no birds, no lizards, no turtles, no crocodiles, no us. Sometimes the rain that destroys is also the rain that nourishes. Sometimes the storm that tears down is also the storm that clears the ground for something new. This is not a justification for destruction, and it would be dangerous to use it as one, but it is a truth about the way life works on this planet. The history of Earth is not a story of steady progress. It is a story of catastrophe and recovery, of collapse and renewal, of endings that are also beginnings, and the Carnian Pluvial episode is one of the most vivid examples of this pattern, and its echoes reach all the way to the present moment. As you lie here, listening to these words, you are living proof that the rain worked, that the catastrophe, as terrible as it was, led somewhere, that the destruction was not the end. Your body, your breath, your thoughts, all of them trace their lineage back through mammals, through the first mammalia forms, through the ecological upheaval of the Carnian Pluvial episode, to a world that was remade by 2 million years of rain. You are part of the story. You are the aftermath. You are what the rain created. When we step back and look at the Carnian Pluvial episode as a whole, one truth stands above all others. The atmosphere is never a passive backdrop to the story of life. It is one of the central characters. It shapes worlds. It creates monsters. It fuels extinctions. It opens doors for new forms of life. And when it changes, everything changes with it. 234 million years ago, the atmosphere changed because volcanoes pumped carbon dioxide into the sky. The warming that followed unleashed rain on a scale the planet had not seen in millions of years. That rain fell on a supercontinent that had been baking in drought, and it transformed it. Deserts turned to wetlands. Rivers carved new paths through ancient stone. Lakes appeared where none had been. Forests grew where bare rock had stood. The plant communities of an entire planet were overturned, and the animals that depended on them were forced to adapt, migrate, or perish. In the oceans, the cascade of effects was equally profound. An acidification dissolved the shells of creatures that had thrived for millions of years. Nutrient runoff from the rain-soaked continents fed algal blooms that consumed oxygen and created dead zones. Carbonate platforms that had been the foundations of marine ecosystems collapsed. A third of all marine genera have vanished. The ocean floor itself was transformed, its chemistry rewritten by the flood of material washing in from the land. And yet from this crucible of destruction, the modern world emerged. Dinosaurs, which had been small and insignificant for 20 million years, seized the opportunities created by the extinction of their competitors and began the explosive diversification that would lead to their dominance over the next 165 million years. Lizards, turtles, crocodilians, and when the distant ancestors of mammals all found their footholds during or after the Carnian rains. Modern coral reefs trace their origins to this period. The great conifer forests that would define the Mesozoic landscape were established. Even the microscopic plankton that today form the base of the marine food web got their start during the Carnian Pluvial episode. It is a story of endings and beginnings woven together so tightly that they cannot be separated, The same rain that killed also created. The same disruption that destroyed old ecosystems built new ones. The same volcanic catastrophe that drove extinction also drove evolution. This is the pattern of life on Earth, repeated over and over through billions of years. Destruction and creation are not opposites, they are partners, each one making the other possible. And the strangest part of all is how hidden this story has been. For most of the history of modern science, the Carnian Pluvial episode was unknown. The great extinction and radiation that reshaped the living world was invisible, buried in the rock record beneath layers of more famous events. The end Permian extinction, the rise of the dinosaurs, the asteroid impact that killed them, these are the stories that fill textbooks and museums. The Carnian Pluvial episode, arguably one of the most consequential events in the entire history of life, was not even recognised until the late 1980s, and it remained obscure for decades after that. It took patient, methodical work by geologists and paleontologists around the world, people who spent their careers studying microscopic pollen grains and chemical signatures in ancient rocks, to piece together the story that we have heard tonight. There is something humbling about that. The most important events are not always the most obvious ones. The loudest extinctions are not always the most consequential. Sometimes the real turning points are quiet, hidden, revealed only to those who look closely enough and think deeply enough to see them. The Carnian Pluvial episode changed the world, and for 200 years of modern geology, nobody noticed. It makes you wonder what else we might be missing. What other stories are locked in the rocks, waiting for the right pair of eyes to find them? What other turning points in the history of life are hidden in the plain sight, overlooked because they do not fit neatly into the narratives we have already constructed? And the history of Earth is far longer and far stranger than we can easily comprehend. And every year, scientists discover new chapters that rewrite what we thought we knew. Close your eyes now if they are not already closed. Let your mind drift back one last time to that ancient shore. The rain is still falling. It has been falling for thousands of years, and it will continue for thousands more. But there is a gentleness to it now, a steadiness. The initial fury of the storms has given way to something more rhythmic, more predictable. The world has adjusted to the new conditions. The forests are growing, the lakes are full, the rivers are running clear. New creatures are venturing out of their hiding places, testing the changed landscape, finding food, finding shelter, finding mates. Life is doing what life always does. It is going on. Somewhere in those forests, a small, lightly built dinosaur, no larger than a dog, is stepping cautiously through the undergrowth. Its ancestors were insignificant. Its descendants will rule the earth. But it does not know that. It knows only this moment, this forest, this rain. It pauses, lifts its head, sniffs the humid air. A fern frond drips water onto its back, and it shakes it off with a quick, bird-like motion. Then it moves on, deeper into the green, disappearing among the tree trunks in the mist. Somewhere in the shallows of the Tethys Sea, a tiny coral polyp is secreting calcium carbonate, building a structure no larger than a grain of rice. It is one of the first of its kind, a pioneer of a group that will eventually construct the largest biological structures on Earth. The water around it is warm and cloudy with sediment, but the polyp does not care. It is doing its work, molecule by molecule, the same work that its descendants will still be doing 234 million years from now, building reefs that will shelter fish and turtles and anemones in a world that this little polyp could not possibly imagine. Somewhere in the damp soil at the edge of a newly formed lake, a tiny mammalia form, a creature with fur and warm blood and the faintest beginnings of what will eventually become the mammalian brain, is sleeping in a burrow. It is nocturnal, this little creature. It hunts insects in the dark and hides from predators during the day. It is small, vulnerable, and utterly unaware of its own significance. But the lineage it carries will outlast the dinosaurs, outlast the great reptiles, outlast the Mesozoic era itself. In the fullness of time, this tiny creature's descendants will build cities, write symphonies, launch rockets into space, and lie in bed at night listening to stories about events that happened 234 million years ago. All of this is growing, quietly, in the rain. The Carnian Pluvial episode lasted roughly 1 to 2 million years. In the context of a human life, that is an incomprehensible span of time. But in the context of the Earth's 4.5 billion year history, it is a brief interlude, a wet season in the planet's long story. A rainstorm that lasted a little longer than most, and yet look at what it accomplished. In that brief window of geological time, the foundations of the modern world were laid. The cast of characters that would define the next 200 million years of life on Earth took their places on the stage. The ancient world died, and the modern world was born, all of it watered by rain that fell from skies darkened by volcanic ash, on continents that no longer exist, in an atmosphere that no longer exists, in a world that has been utterly transformed by the passage of time. It is one of the most remarkable stories in the history of the Earth, and yet until very recently, it was almost completely unknown, a hidden turning point, a secret origin, a 2 million year rainstorm that nobody talked about, because nobody knew it had happened. Now you know. And tonight, as you drift towards sleep, you carry that knowledge with you. You know that the dinosaurs owe their rise to the rain. You know that the coral reefs that fringe tropical islands today trace their ancestry to the Carnian crisis. You know that the mammals, your own distant relatives, they found their first foothold in a world being remade by volcanic fire and relentless water. You know that the atmosphere is not a backdrop, but a character, one with the power to reshape the entire living world in the span of a geological heartbeat. And you know that sometimes the most important stories are the ones that nobody tells, until someone does. The Carnian Pluvial episode was sandwiched between two of the largest mass extinctions in Earth's history. The Permian Triassic extinction came before it, killing more than 90% of all species. The End Triassic extinction came after it, roughly 30 million years later, wiping out many of the groups that had diversified during the Carnian and clearing the way for the full flowering of the dinosaur age. The Carnian sits between these two catastrophes like a quiet hinge, and a turning point that most textbooks skip over entirely. But the Carnian Pluvial episode was not just a footnote. It was the moment when the old world died and the new world was born. It was the dawn of the modern world, as the scientists who study it have said. And its echoes are everywhere, if you know where to look. In every pine tree on a hillside, in every lizard sunning itself on a wall, in every coral polyp building its tiny home in a tropical sea, in every bird singing in the morning, in you. Now let the rain fade, let the ancient world grow quiet. Imagine one last time that you are standing at the edge of a Carnian forest as the last great pulse of rain begins to weaken. The clouds are thinner today than they have been for as long as anyone can remember. There are breaks in them now, in places where the grey gives way to a deeper blue that no creature on this landscape has seen in thousands of years. The rain is lighter, not a downpour, but a drizzle, the kind that barely makes a sound as it settles on the broad, flat needles of the conifers around you. The air is still warm, still heavy with moisture, but there is something different about it. A faint dryness at the edges, a hint that the atmosphere is beginning to exhale, to release its grip on the water it has held so tightly for so long. The forest around you is dripping. Every surface is wet. Water beads on the bark of the conifers and runs in thin streams down their trunks. It pools in the cups of fern fronds and drips from the tips of leaves. The ground is soft, saturated. You're covered with a thick carpet of decomposing plant matter that has been accumulating for millennia. The smell is rich and complex. The deep, earthy scent of wet soil and rotting vegetation and new growth all mixed together into something that is both ancient and alive. A stream runs nearby, its banks overflowing, its water a murky brown that speaks of the sediment still being washed from the hills. In the shallows, small fish dart between the roots of plants. their scales catching the occasional shaft of sunlight that penetrates the canopy. Further out, in the deeper water, something larger moves, a shadow beneath the surface, a predator waiting for prey to come within reach. The ecosystem of this stream is new, assembled from the survivors and pioneers of the Carnian crisis, and it is still finding its balance. But it is alive, and it is growing. The storms are passing, as all storms do. The skies over Pangaea are beginning to lighten, just a little, just enough to let a sliver of warm sunlight through the clouds. The forests are dripping, the lakes are full, and the air is thick with the smell of wet earth and new growth. Somewhere, a dinosaur calls out, a sound no human ear will ever hear, but a sound that marks the beginning of an age. Let that image hold in your mind as your thoughts grow soft and your breathing slows. The rain is easing, the world is settling into a new shape, and life as it always does is beginning again. But if you thought that the Carnian Pluvial episode was the most dramatic event in the Triassic, if you thought that 2 million years of rain was the worst that this period of Earth's history could produce, then I should tell you that there is more to come, because the very dinosaurs that rose from the Carnian rains would face their own trial before the Triassic was through. Not rain this time, but something else entirely. The end, Triassic extinction, driven by yet another massive volcanic eruption. The Central Atlantic magmatic province would sweep across the planet roughly 30 million years after the Carnian rains ended. It would kill many of the competitors that still shared the world with the dinosaurs, and it would clear the way for the true age of dinosaurs, the Jurassic, to begin. And beyond that, in the depths of time yet to come, another catastrophe awaits. Not from volcanoes, but from the sky itself. A rock the size of a mountain, hurtling through space at 20 kilometers per second, is on a collision course with a planet that does not yet know what a dinosaur is. That impact 66 million years ago would bring the age of dinosaurs to an explosive end and open the door for mammals, including the ancestors of the creature lying in bed right now, listening to this story, to finally step into the light. But those are stories for another night. For now, let the rain carry you. Let the ancient world cradle you in its warm, wet arms. Let the sound of water, falling gently on ferns and stone and the surface of lakes older than thought, be the last thing you hear as you drift into sleep. The rain that fell 234 million years ago is still falling, in a way. It falls in every ecosystem that traces its roots to the Carnian. It falls in every descendant of the creatures that survived and diversified during those 2 million years of moisture. It falls in the patterns of life and death and renewal that have repeated themselves over and over across the vast span of Earth's history. And it falls tonight in the quiet space of your imagination where ancient storms and modern dreams meet. Thank you for joining me on this journey. Thank you for letting me share this quiet corner of science with you. Sleep well, dream of ancient rain and forests growing and a world remaking itself in the most extraordinary way. Good night, friends, and remember, the next time it rains where you are, the next time you hear the gentle patter of water on your window, or the distant murmur of a storm rolling in from the horizon, think of the Carnian. Now think of the rain that fell for 2 million years. Think of the deserts that became forests and the forests that became the foundation of everything. Think of the tiny dinosaur stepping through the undergrowth, not knowing that its descendants would inherit the earth. Think of the coral polyp building its first tiny reef. Think of the small, furry mammalia form sleeping in its burrow, dreaming whatever ancient dreams such creatures dreamed, not knowing that one day, 234 million years later, one of its descendants would be lying in a warm bed, listening to this story and drifting peacefully off to sleep. The rain connects us. Across all that impossible distance of time, the rain connects us. It fell, and the world changed, and here we are. Sleep well. I will see you next time.